Okay, thanks everyone. I'm going to be talking today about the Exoplanet Climate Infrared Telescope, or EXCITE experiment. And as I mentioned, I'm from Goddard, but here on behalf of a large team, which I'll get to a little bit later. So what is EXCITE? EXCITE's a half-meter balloon-borne infrared telescope. The science instrument on the back end is a cryogenic IR spectrograph, which operates from about 0.8 to 4 microns with a native resolving power of about 50. The gondola that we fly is a very close copy of the successful Suborbital platform with some differences that I'll cover. Primary science is to perform a near-infrared spectroscopy of hot Jupiter-type exoplanets. Core science case is doing what's called phase-resolved spectroscopy. That's continuous observations of an exoplanet as it orbits its host star. But we also get the well-known atmospheric discontinuities in the orbit that are well-studied, the transit and the eclipse. These measurements are difficult. They require long stares and excellent photometric stability. So that's basically the core of our design. Also EXCITE, not just a science mission, but we fly a lot of new and advanced technologies that will be enabling for future low-cost and high-precision exoplanet science missions with a number of technologies that flew first in EXCITE and will be in orbit in the next 1 to 2 years. We recently flew an engineering flight about a year ago and are prepping for a long-duration science flight from the Antarctic. So what is a phase curve? So if you look at the cartoon in the middle, the phase curve is basically the continuous observation of a transiting exoplanet as it goes about its host star. And we're focused specifically on hot Jupiters that are tidally locked. And so if you do this measurement, you measure a light curve, kind of like shown. If we start right in the middle of the cartoon, that's when the exoplanet is between us and the host star. So you get a discontinuity in the light curve at the transit. And then as the planet goes around its star, you see more and more of the hot day side of the planet. So you measure more and more flux, and then it disappears again behind the star. So those measurements, in contrast to just the transits or the eclipses, you're able to measure the entire energy budget of the planet. You can measure atmospheric circulation because you can see how the temperature changes as a function of wavelength and get down into the depths of the atmosphere. Being in the near-infrared, we get a lot of spectral features from interesting molecules, hydrogen and carbon containing. If you go out far enough in wavelength, beyond, say, 1.5 or 2 microns, you can get the peak of the planet's thermal emission and actually nail down its temperature. This is all done spectroscopically, so it's as a function of pressure, and you get the discontinuities that are well studied essentially for free. So some of the information derived, so what you do is you'll take a phase curve measurement, you'll look at how the sinusoidal maxima and minima are separate from the geometric ones, and that's going to tell you if everything were perfectly in line, I would say there's no energy redistribution at all. But you'll see certain things will lag at different altitudes and different pressures, and so you're getting a picture of how energy is actually moving around in the atmosphere of these planets. And from those measurements, you can do things like generate these spectra shown at the right. This is data from Hubble showing what the actual emission spectrum of the planet looks like as a function of orbital phase. And from there, you can derive temperature and pressure profiles of the atmosphere. So it's a very scientifically rich measurement, but it's difficult and time-consuming. These orbits are a couple days at a time, and that's especially difficult to do from low Earth orbits. So I'd say this is one of the situations where the science is hard from space, but it's really ideally suited from a suborbital platform that deploys from near Earth's poles because there are many targets in the sky never set. So you can have a very stable observing platform, and you can point and stare and get a 2-day phase curve in 2 days instead of hundreds of hours of space telescope time. So going into that with a little more deeply, the plot at the bottom left, this is actually reduced data from Hubble of a one hot Jupiter exoplanet, and you can see just the settling time of the instrument as it goes around the Earth every 90 minutes, has to reacquire the target and then stare. You get, with our eyes, we can see kind of a periodic signal there, but I'd say it's also statistically consistent with a straight line. So that kind of illustrates that even with a giant aperture in space, it's not a very good way to make the measurement, or not the ideal way. The other problem is that measurement took, I think it was about a 20-hour period planet, and it took over 100 hours of space telescope time to get that. So not only is it hard and difficult to reduce the data, but it's inefficient. But from balloon altitudes in the near infrared where we're looking, Earth's atmosphere is transparent, very stable. And you can just basically pick a target in the southern sky and point and stare. 2 days later, you have your phase curve, you move on to your next target. So just overall science impact of what EXcite can do. On the left is just a list of, there were a ton of planets, hot Jupiter planets that were discovered with the WASP telescope in the southern hemisphere. Most of those are accessible to EXcite, a lot of them never set. And on the right, a sample physical parameter space. So the two X's that you see there are the first two spectroscopic phase curves that were in the literature. I think there's been maybe one or two more that have been published since that plot was made. And all the different planets are things that we can observe with high signal to noise in a single long duration flight. So going from 2 to 10 plus in a single flight. So getting into the actual payload itself. So the gondola, as I mentioned, is based on what was flown on Superbit. We control 3 axes to better than an arcsecond RMS with just in terms of gondola stabilization. And then we can stabilize the line of sight at our focal plane to about 50 milliarcseconds RMS using a optical tip tilt mirror. The science instrument itself is a 2-channel cold spectrometer. We use a prism to get a native resolving power of about 50. We have an HGRG focal plane, which was left over from JWST NIRSpec, read out by the Acadia readout electronics developed at Goddard for the Roman Space Telescope, and Macy warm electronics. And the optical ray trace at the bottom left kind of gives you an idea of what the signal path is. We have our telescope, then the tip tilt mirror, which is going to do our fine beam steering, drive it into our cryostat, and then pretty simple spectrometer. More details about the gondola. It's pretty much like Superbit, but there are some differences to accommodate the differences in our back-end instrumentation. Superbit, I think, Stephen could correct me if I'm wrong, had no moving parts in the back or no actively moving, but we're cryogenic and we have a pair of cryocoolers. So we have to both deal with the vibrations from the cryocoolers and also get rid of the heat that's dissipated by them. Each cooler dissipates about 150 watts. So we have to get all that heat from the back end of the instrument across all of these nested frames and then radiate it out to space. So we have several systems on the gondola designed to do that. And then otherwise, I would say the performance is about the same. A couple constraints in how basically we can look between 22 and 60 degrees to avoid seeing the ground or the balloon and basically point anti-sun. But even within those constraints, all these targets are still continuously visible for the duration of a flight. The telescope, also similar to what was flown on Superbit, a couple optical differences. It's a 1/2 meter primary. Secondary has actuation for tip and tilt and also focus. I'd say probably the biggest difference in terms of how we use it versus how it was flown previously is we try to passively cool our optics as much as we can. So we do have the interior wrapped with MLI. Could be a problem for stray light in the optical, but for the infrared, it's necessary to get to the cold temperatures that we want. On to the receiver. So the receiver, this is what's bolted to the back of the telescope. It's kind of the core of our science instrument. Basically consists of 3 components: the cryostat, which cools the spectrometer and the detector system. This whole assembly is bolted to the back of our telescope via a component we call the transfer box, which is effectively an optical bench. So not only does it bolt the receiver to the back of the telescope, but it also grabs the tip tilt mirror and the fine guidance camera. And it's a pretty cool component. We used a generative design approach, which is basically, some people would call it an AI approach. But it came up with a design which met all of our constraints, but made it a lot stiffer and lighter than we were able to do with conventional design. So happy to give more detail about that to anyone who's interested. Inside of the cryostat, there is the spectrometer and then detector system as well. So for the cryogenic system itself, we use a pair of pulse tube cryocoolers to get those temperatures. We thought about other cooling solutions. There are other cryocooler technologies. They're liquid or solid cryogens. None were really able to meet the optimization that we needed. And particularly pulse tubes are nice because compared to other cryocooler technologies, they have fewer moving parts and then less exported vibration. So this was their first implementation, first time they ever flew on a balloon payload with a couple just design ways to keep these things not interrupting our pointing, because again, 50 milliarcseconds is a small number, so you don't really want any vibrations, but keeping the pistons moving along the bore side axis helps somewhat. And then the electronics that we use to drive them have both passive and active vibration cancellation using feedback from accelerometers that are bolted to the coolers. So overall, through all of our testing and through our flight, we've measured 0 negative impact from the coolers on the pointing of the instrument. The heat dissipated by the coolers, so both coolers dissipate about 150 watts apiece. We need on the ground, convection is almost good enough not to burn up your coolers. Of course, in 3 millibar atmosphere, that doesn't work anymore. So we have a pumped methanol fluid loop, which basically will take, we have heat exchangers at the components of the cryocoolers that get hot. And we basically pump that heat to the big radiators at the front and send that off to space. So that is our scheme there. And you can see also, this kind of gives you an idea of what the allowable envelope was to put the whole receiver. So this whole cryostat, I think it's 14 inches in diameter and about this big, this tall. So it's quite an impressive and compact unit. Here's a picture and a ray trace of the spectrometer. So light from the telescope is, we have a fine guidance optical camera and a dichroic that sends the infrared light into our telescope. It basically passes through, gets collimated by an off-axis paraboloid mirror, goes into a prism, disperse the light, and then we use a dichroic to disperse into a long wave and a short wave channel. We split it at about 2.5 microns. The short band is where we're always background limited by our host star. The longer band, we have more, we have to worry about thermal emission from our own optics. So we split those. It makes data reduction easier if you don't have those two overlapping. The whole optical bench and a lot of the optical mounts are custom designed and machined out of titanium, which is a pretty low CTE material, not like an NVAR, but low enough so that we can align the spectrometer once at room temperature, and it maintains alignment all the way down to its 100 Kelvin operating temperature. And then there's the detector assembly, which you can see in the picture, has that tall box with a trap on top of it. That's thermally isolated, but rigidly mechanically mounted to the optical bench through some Kevlar suspensions. So that, again, will maintain its alignment as the thing cools. Detector system. So we're using it's a flight candidate detector left over from near spec that we're using. Well-characterized detector, and we're reading it out using the Acadia electronics. There's a picture of well, it's not the detector, but it's the detector box. And we put 2 band-defining filters on the front of it because we don't actually get science all the way out to 5.3 microns due to Earth's atmosphere and thermal emission. So into our engineering flight. So we flew last fall, about a year ago, had a nice long flight, at about 7.5 hours at an altitude of more than 39 kilometers. And I'd say that everything worked basically as designed. We were able to stabilize the gondola to each frame to better than an arcsecond RMS, which is what we were going for. Detector system, nothing much, all performed nominally. The whole H2RG plus Acadia, that was the first time those two had been put together, and Macy all worked fine. And that system, the Macy, that was, as I mentioned, the first flight of Acadia in the space-like environment. Also first flight of Macy, and Macy's has been adopted by several other orbital experiments. I think the first one should be Pandora, which is going to launch soon. And then the cryogenic system also met all requirements with significant margin. I'd say that was the one that I personally was really interested to see how it would do, because without convection, it really all depended on how much heat we're actually sucking out with our fluid loop. And it turned out that, as you would expect, but with the radiators actually seeing 2.7 Kelvin instead of 300 Kelvin, everything operated about 20 degrees colder at float than it does on the ground, and the performance was excellent. A couple issues that we did have, I'll talk about the mitigations in a second, is the GPS compass, which is provided by the launch provider, failed basically at the balloon launch, which limited our ability to know our azimuthal position when we were in flight. And then our elevation axis of the telescope had limited travel. I'd say about half of what it was designed to do due to some maybe it's probably more like better called thermoplastic deformation of a bearing housing. But we've since implemented both hardware and software changes to fix those things, and then if they were somehow to happen again, to mitigate their impact. Okay. So into where we are now. So we flew. We had fortunately sustained very minimal damage to the payload on termination, landing, and recovery. Show that the picture at the top left is just after we deployed the parachute. That orange or reddish thing at the top is the parachute. So it fell back down to Earth and landed at the right, somehow upright. It was at about a 45-degree angle on the side of a mountain, but didn't tumble into the ravine below, which is great. And it actually took a helicopter to get it out of that spot. But throughout all those actions, nothing really broke, which was excellent. But we did have a lot of refurbishments that we've done since then and are basically wrapping up now. Cleaning our optics, rebuilding the elevation drive motors, some adjustments to the cryocooler power supplies, and then installed our solar array. So that covers most of the things that we had issues with. We also built and are currently testing pinhole sun sensors, which will give us redundant azimuth information for our next flight. So if a system does drop, we'll have a backup. Basically, next thing to do is install the science detector, which is going to be happening in the next couple of weeks. And there's an instrument paper being written by Tim Ream, which is going to cover basically a lot about our instrument design results from the test flight, and then revisiting our noise models and updating them with the as-built instrument. So that's should be available pretty soon here. And I will finish there and just acknowledge, obviously not possible without the rest of the EXcite team. It's a bunch of people at a bunch of institutions across the world. So thank you for listening.